Hello, today we have this problem. We have to find a natural number n, given that the product of all of its positive divisors is equal to n cubed minus 14n. So let's begin with the fact that if we were to factorize n, and afterwards we can express n as a product from I equals 1 to m of pi to the power of xy, where pi is prime, xy is part of the set of natural numbers. That is how you would factorize any natural number other than 1. So now that we have this established, we have to express the divisors somehow. Thing is, divisors can be easily expressed by, let's say there is some sequence A for every divisor, and let's say that a of I is less than or equal to x of I, and let's say that if I belongs to the set of natural numbers I plus the set containing 0, because for example 1 is a divisor of, for example, 7, and etc. So now that we have this part, it's only natural that we would want to find all possible a of I, or furthermore, try to express the product of all of these unique expressions. So let's begin by trying to find the individual primes. Let's say that the product of all divisors is capital M. It's equal to the same primes but with some other sequence. Let's call it B of I. Now we need to find B of I for just okay, B of I. Now let's begin with finding the amount of divisors this number has. For convenience sake, you'll see why in a second. So the amount of divisors number has is gonna be product from I equals 1 to m of xi plus 1. That is related to this equation over here. Not equation, expression. The vocabulary gets checked up. Sorry. So that means we need to account for every possible sequence like that. That would suggest that we need to just go through a of I from 0 to x of I. And now that is fairly simple. We just say 0 plus x of I, and now we need the amount of elements in this progression, the x of I plus 1. I need to divide it by 2, so that's going to be x of I times x of I plus 1 over 2. But wait, this isn't just it. Let me explain why. Thing is that for every part of this sequence, there's also the rest. We have found unique examples of a of 1. Now, to compensate for the fact that there are going to be more occurrences of a of 1 be equal to some number than just 1, need to find the amount of ways we can organize the rest of the sequence, which is gonna be just this, except we're gonna modify it a little. We will say that this goes, let's do another variable, because we have I occupied already. Say we have j, x, g, and here we say I minus 1. We're gonna multiply it by this, except we start from I plus 1 up to m, and this over here will actually result in the set sequence. That will be actual true statements, but it's very annoying to work with, so we're gonna simplify it further. Notice how from this multiplication, to make it just from 1 to m, we have this exact element missing. So what we're gonna do is we will borrow it from here. And here we go. 1 to m of x j plus 1. Now this is an expression you have seen before, which is this. Let's say that the amount of divisors this number has is letter D capital. So in the end what we have is x of I times D capital over 2. Okay, let me write this nicer. So let's go back in and substitute in. Now that m capital is equal to this, and we have found b of I, which is x of I times d over 2. Now, thing is, d over 2 is not dependent on I, so we can bring it out of the product. And guess what we have here? We got the product that we defined to result in the number n. So, in other words, the product of all divisors of number n is going to be n to the power of d over 2, which is handy knowledge. Now, let's rewrite that equation. M equals n cubed minus 14n. And we know that m is also equal to n to the power of d over 2. So let's divide both sides by n. We know that n is natural, so it can be 0. That's n to the power of d over 2 minus 1 equals n squared minus 14. Now let's transport all n's to one side and leave 14 at the other. N squared minus n to the power of d over 2 minus 1 equals to 14. Now let's bring out n squared here. You'll have n squared times 1 minus n to the power of d over 2 minus 3 equals 14. Let's do another substitution. Let's say that t is equal to d over 2 minus 3. And the thing is, t essentially belongs to the set of numbers like this. In other words, it's always going to be either a whole number or whole number if you were to multiply it by 2, which is handy knowledge here. I will apply it in a second. So now thing is, we have this product here. Let's copy paste it here, substitute t in. And thing about it is we don't want this bracket to be negative, or else this can be true, because n squared is always greater than or equal to 0. Therefore, 1 minus n to the power of t is also greater than or equal to 0. Furthermore, we can get rid of this not strict part, so we can use a strict inequality. Now, we know that n is not equal to 1. You can just substitute in and it won't work. So if n is not equal to 1, n is a natural number, so it's always going to be greater than 1. And that would suggest that 1 minus n of t is going to be less than 0 if t is greater than 0. In other words, we know that t is less than or equal to 0. Now, let's return to the way we define t. It's d over 2 minus 3, and the minimal value of d is 1 for the number 1, but obviously we're not reviewing that, so the minimal value for d is going to be 2 divisors. Any prime number has 2 divisors. Any number that's not prime and not 1 is going to have more positive divisors. So t is going to be greater than or equal to minus 2. So we gained an actual bound. Now that t lies between minus 2 and 0 included. And do you know what that means? It means that we can just go through the variance from minus 2 to 0. So let's start. If we were to plug in minus 2, we will have n squared minus 1 equals 14. Obviously it does not match, so let's underline this. Let's continue. N squared minus n to the power of 1 over 2 equals 14. Now let's say that is going to be n squared minus 14 equals square root of n. Let's square both sides. N to the 4th power minus 28n plus wait a second. I think it's 196. Okay, yeah, and that is going to be equal to n. Okay, there's a square here. N to the 4th power minus 28n squared minus n plus 196 equals 0. Now, let's review one thing about the case we're reviewing. T equals minus 1 over 5. It will mean that d over 2 minus 3 equals minus 1 over... Okay, why did I write minus 1 over 5? It's supposed to be minus 3 over 2. So let's multiply both sides by 2. Maybe d equals 3. And for a number to have 3 divisors, it has to be a square. So we know that n is some number k squared. K is a natural number. Now let's head back here. We don't have to deal with these huge polynomials. We can plug k here. You can say that this is gonna be k to the 4th power here. Just k here. K to the 4th power minus k, minus 14 equals 0. Now, according to the rational root theorem, the possible roots of this polynomial that are rational are going to be plus minus 1, plus minus 2, plus minus 7, and plus minus 14. So we don't need negative roots, not even going to try them, since we're looking for a natural solution. So let's go one by one. We have to plug in 1, 2, 7, and 14. Plugging in 1, it's obviously going to be a negative number. Plugging in 2, that's going to be a correct solution, actually. That results in 0. Plugging in 7, it's obviously going to be greater than 0. Same for 14. So we know that k equals 2. N equals k squared equals 4. Cool, we found a solution. Now we still have quite a few to check. Negative 1, that's going to be n squared minus n equals 14. It's a quadratic. And if we were to find the discriminant, d equals 1 plus 56, that's going to be 57. This is not a natural square, so obviously it doesn't have necessary solutions for us. Let's continue. Now, I review 0 first, it's just simpler case. If it's 0, then we were to plug it in, that just results in 0 here, and obviously does not match. So we have only one case to review, that's minus 0.5. We have n squared 1 is n to the power of minus 1/2 equals 14. N squared minus n to the 3/2 power equals 14. Now let's review something we already know about this. T is equal to negative 1/2. D over 2 minus 3 equals negative 1/2. Therefore, D equals to 4, which would mean that... Actually, wait, I think I messed up. Yeah, D is going to be 5. Now, again, factorization of 5, the only one we can do is 5 equals 5 times 1, so this is going to be just k to the 4th power. 4 plus 1 is going to be 5. N equals k to the 4th power. Let's sub it in. K to the 8th power minus k to the 6th power equals 14. Let's do another substitution. Let's say we have some number y equals k squared. So y to the 4th power minus y to the 3rd power equals 14. Let's transport 14 to the left side. Now again, applying the rational root theorem, we need to check these cases. Plugging in 1, this is not a solution. Plugging in 2, that's not a solution either. Plugging in 7 is way too much. Same for 14. Now actually, I want to check this more thoroughly because I'm not entirely sure about it. Let's factorize it a little. Y to the 3rd power times y minus 1 minus 14 equals 0. This has to be greater than or equal to 14. Now, okay, so this is obviously going to be greater than 14, and this too. Cool, we have found the only solution, n equals 4. We can check it. The factors of 4 are 4, 2, and 1. Now the product of them is going to be 8. 4 to the third power is 14 times 4 is 4 times 16 minus 14. And that's just going to be 8. Cool. We have solved the problem. That's it for today, yeah. I hope I did not overcomplicate it too much for you. Bye.